In this video, we look at chapter 5.2, all about inner product spaces. So here are our learning objectives for the videos. We're going to have these learning objectives separated out into 3 videos for this section. So we are going to determine whether a function defines an inner product. We're going to find the inner product of 2 vectors in a variety of different fields. So we're going to look at Rn. We're going to look at M n by n, the set of m by n matrices. And we're going to look at Pn, the polynomials of degree n or less, and then also C in the interval AB, so that's the set of continuous functions in the interval AB. So these 4 fields we'll look at finding the inner product in. We're going to use the inner product to find angles between 2 vectors and determine whether the vectors are orthogonal. Remember, the vectors will be orthogonal if the angle is 90 degrees, and so we'll find if the inner product is 0, then the angle will be 90 degrees or pi over 2, and then we'll have an orthogonal relationship. And then we're going to find an orthogonal projection of a vector, so this is a new term for us, onto another vector in an inner product space. An orthogonal projection is just what it sounds like. It's projecting a vector at a right angle or 90-degree angle onto another vector. So the inner product is an extension of the concept of the dot product from Rn to a general vector space. So in Rn, what we thought of as the dot product is a type of inner product, and it's actually what we call the standard inner product. But when we come to a general vector space, we generalize the concept into this idea of inner product spaces. So the standard dot product, I wrote it down here in R2. It is over here on the left, so it's just our standard dot product in R2. And to indicate inner product, you'll notice we use these brackets on the outside. So that's kind of the symbol to note the inner product. And then in Rn, here's our inner product sideways brackets again. It's just, again, our standard dot product rule. So we wrote it here as column vectors. You could have them as row vectors. It doesn't really matter in Rn how you represent the vectors. So the standard dot product is also called the Euclidean inner product because it's the inner product on Rn, and we know Rn is known as Euclidean space. And so that's written U dot V, while the general inner product on any vector space is written UV with these brackets on the ends. I'm not sure the name of the brackets. They look kind of like sideways carrots, or the pointy brackets, you could call them. You don't have to be too technical. So let's take a look at the definition of inner product. So you're going to see it's the same definitions that we had for dot product, but extended to any vector space. So we're going to let U, V, and W be vectors in a vector space V, and C is going to be any scalar. An inner product on V is a function that associates a real number UV in the inner product brackets with each pair of vectors U and V and satisfies the following axioms. So the symmetry axiom is first here. Doesn't matter what order U and V are in the inner product, you're going to get the same results. And these are going to equal a real number once we do our calculations. Then we have the distribution property here. So property 2. If you've got U inner producted with the sum V plus W, then that's the same as U inner producted with V plus U inner producted with W. And then we have scalar multiplication here. So if you've got a scalar C multiplied by the inner product UV, that's the same as the scalar C multiplied by U and then V in the inner product. Notice it doesn't go quite as far as the dot product. In the dot product, we could have that scalar C multiplied by either part of the inner product, but for the general definition of the inner product, that scalar C is just multiplied by the first vector when you distribute it through, and we'll see that in action in our examples. And then the inner product is always non-negative, so the inner product of V with itself is always greater than or equal to 0. So if you're inner producting something with itself, it's non-negative. Of course, we know the dot product can be negative if you are working with different values. And then the inner different vectors, right? But if you're inner producting something with itself, you're going to get non-negative results. And then the inner product with some of a vector with itself is 0 if and only only if the vector is 0. And a vector space V with an inner product together, they're known as the inner product space. So to have an inner product space, you have to have the vector space, and you have to have the inner product, which is kind of like a rule. So you can think of the inner product as, you know, a rule that together with the inner product rule and the vector space, you get this inner product space. So let's take a look at some examples here. So we're gonna look at an example in R2. So we're gonna have U be U1, U2, and V is V1, V2. But instead of the usual Euclidean inner product, which we can write as U transpose V, because we just, you know, multiply them through like column or row matrices, then we're gonna define as an alternative here, the inner product is gonna be U transpose multiplied by this matrix 2, -1, -1, 3 multiplied by vector V. So when you go through that multiplication, you get these results here, that V is going to follow this formula of 2 U1 V1 minus U1 V2 minus U2 V1 plus 3 U2 V2. And the 2's and the negatives and the 3 all come from the values in this extra matrix here that we have added into our equation. So we want to show that this inner product definition UV is in fact an inner product. So we have to work through all 4 properties to verify. So our first property is to check the symmetry. So we're going to check the inner product of V and U in that order, because we know UV up here is what we've got circled in yellow. So then we're going to have V transpose multiplied by our matrix 2, -1, -1, 3 multiplied by U. So that works out to be 2 V1 U1 minus V1 U2 minus V2 U1 plus 3 V2 U2. And we know since we're in R2, these components are just real numbers, which we can multiply in any order. So voila, these are equal to the inner product UV. So we have the symmetry property. All right, in part 2, we're gonna check the distribution property. So we know for matrix multiplication that U transpose A multiplied through by V plus W is going to be U transpose A work together first with the parentheses multiplied by V plus A, and then we know we can distribute the U transpose A through to V and to W, and then we know we can do this without the parentheses in any order like this. So then that just gives us UV inner product and UW inner product. So we have shown that property 2 holds, the distributive property. So now we take a look at property 3. This is to show that scalar multiplication property holds. So the scalar C times UV is going to be C out front multiplied by our inner product here. And then by properties of matrix scalar multiplication, we know that C can get multiplied by U transpose, which is just C U inner producted with V. So now we just have the last property to check here. So I'm calling this solution part 4. And this is where we check V inner producted with itself. So that's going to work out to be all of this. Oops, I went a little too soon to circle here. All of these values, oh, here and here, okay. So I can rearrange to get this grouping in the second circle. So the first grouping, I'm just calculating through the inner product space, and we get 2 in the middle term because we have 2 of the minus V1, V2s. We are going to complete the square here with the second part now. So what we're doing is we're splitting up the 2V1 squared. So we've got a V1 squared over here. And then in the second part of V1 squared that we're going to use to complete the square, and or just rewrite as a square. And then we took the 3v2 squared and pulled out the plus 2v2. And so we've got just a plus v squared over here. So we get to rewrite the second part as, in factored form, v1 minus v2 all squared. And then we've got the extra v1 squared plus 2v2 squared. This is non-negative because these are all squares. So what completing or factoring into a square does is it shows us everything is greater than or equal to 0. And then we know the only way we're going to get a 0 here is if components v1 and v2 are both 0. And so that gives us the fact that the only way we're going to get a 0 is if the v is a 0 vector. Okay, so we've proven part 4. So we have verified that uv here is an inner product space. So the inner product spaces don't have to be just our usual dot product definition. Other definitions, even in Euclidean space R2 or Rn, are going to meet the properties of dot products, of inner product spaces, besides just the dot product. Okay, let's look at this example also. So now we're in R4. So here we are in R4. We're going to let U be UT through UZ, and we're going to let vector V be VT through VZ. So instead of the Euclidean inner product, U transpose V, we're going to let the inner product be U transpose this matrix with a negative C squared in the first component, and everything else is 1. So it's almost the identity matrix, but it's going to give us this negative C squared. It gets multiplied by the first components UT and VT. And so this all gets multiplied by vector V. And C is going to be a positive constant. It's what we would think about as a speed of light in physics. So when we expand our inner product here, we get U inner product with V is negative C squared UTVT plus everything else is just singular because the 1's here on the diagonal. It's just like the identity matrix in the rest of the matrix. So plus UXVX plus UYVY plus UZVZ. So we want to show that this is actually not an inner product. And this has a name. It's known as the space-time interval. So if you take a astrophysics class, you'll get to study this. So the property that doesn't hold is property 4. So remember, to show that something is not an inner product, you just have to show that one property doesn't hold, and then you have shown that if one property doesn't hold, it's not an inner product space. So we are going to look at what happens if you take V inner product with itself. So when you multiply through, you get this result, negative C squared VT squared plus Vx squared plus Vy squared plus Vz squared. And that can be less than 0. So here's an example. If V is 1 and then the rest of vectors are 0s, you're going to get negative C squared. So axiom 4 doesn't hold. And then there's a note here that axioms 2 and 3 are actually satisfied because of the rules of matrix multiplication. And axiom 1 is satisfied because the symmetry in this matrix, so we know A transpose is going to be the same as A. So again, you only have to show that one of the axioms or properties doesn't hold to show that it's not an inner product space, even if the other 3 axioms or properties hold. So here we showed that part 4, the property of being non-negative does not hold. Okay, let's do one more example. So we're going to let A be the usual 2 by 2 matrix, A11, A12, A21, and A22 as the components. And B will be the usual 2 by 2 matrix with B11, B12, B21, and B22 as components. And these are matrices in the vector space M 2 by 2. Then we're going to define the inner product here. Okay, so our inner product space is going to be A11, B11 plus A12, B12 plus A21, B21 plus A22, B22. Let's verify the properties. So property 1, symmetry, we can show here. A inner product B is going to be able to be rearranged so that we have all the B components first in the multiplication because these are real values. And then that's the same as B inner product A. So it's important to note that multiplication of matrices is not commutative. This is not actually matrix multiplication. If you look at how our inner product is defined with the A11, B11, this is component-wise multiplication, which is different than matrix multiplication. Okay, property 2, we're gonna let W be a third matrix here. So W is gonna be W11, W12, W21, and W22, another 2x2 matrix. And then we see here if we take A inner producted with the sum of B plus W, we can use a distribution of real numbers here to distribute all the A's through what we've got down here in the second row. And then we can regroup as we did in the third row and end up back here at inner product of A and B plus the inner product of A and W. So that regrouping is due to the real numbers that are these values from the components being able to be multiplied in any order. So we're making use of properties of real numbers there. And then property 3, if C is a scalar, again, we can just distribute it through and regroup in here because of properties of multiplication of these real numbers that are the components in the 2x2 matrices. And then CA inner producted with B is our result. So we see that property 3 holds. And then property 4 here, the non-negative property. Well, we know the square of a number is going to be non-negative. So these are just all the same values, the components of B squared, if we inner product B with itself. So we've got the greater than or equal to 0 property or non-negative property met. And then the only time you're going to 0 here is if each component of matrix B is 0. And so that's only true if B itself is the 0 matrix where each component is 0. Okay, in the next video, we'll take a look at the properties of inner product spaces.